In this video I will show you more examples for structs. In the last video where I introduced structs, you already saw in the end this example. And this example is interesting because now we actually do have two members of different types. This first member, string, has some array type, and the second member, value, an integer type. Now, as before, we do have a local variable, foo, of this type, and in this example, it also gets initialized. Now, let's again begin with visualizing the memory location for this local variable when we entered function main. So we do have some part of the memory where a block of memory, a memory location, gets reserved for this variable foo. Let's say this block. So this is the memory location for foo. Now this variable foo has two members, a member str and a member val. Then this would be the memory location for foo.str. This array with 12 characters, and because each character has the size of 1 byte, this memory location would have the size of 12 bytes. And the second member would have the size of an integer, and on my machine an integer would have 4 bytes. Okay, and then we also initialize this variable. The first member gets initialized with the string Michael. Let's denote this for now like that. And the second with 42, of course. Now, about this first member, how it gets initialized, this description usually is good enough for most purposes, but here I actually want to go a bit into the details, because you see, this first member is actually an array with 12 characters, and this string Michael has 7 characters, and then we also have this 0 terminating byte. So in total, this string would have 8 bytes. And this string actually gets 0 extended, and here I want to tell you why, what is actually going on. If you have a string in an initializer, it's actually treated as if you would have an initializer list with the single characters in this single quotes, like that. And then one additional byte, the 0 byte. So you would have an initializer list with 8 elements. And then this initializer list here gets used to initialize the first member, and this value 42 gets used to initialize the second member. And then we can actually look into the memory for this particular part, zoom into this memory location. So down here we would have this 12 bytes, where the first byte gets initialized with the ASCII value of this uppercase M and so on. So this would be 7 boxes. Then we have this 0 terminating byte, and then 4 additional bytes, which are all 0. And these 4 additional bytes were added by the compiler to this initializer list. And then we have pretty much all details that are relevant here in one picture. In this example, things become a bit more interesting, because now we do have an array where the elements do have this type foo. And with this example, I want to give you an idea that sometimes it's not relevant to describe each and every detail with pictures describing the memory locations. Sometimes you just need a few rough details from that visualization. Sometimes it's better or more helpful, more useful to describe it on a higher level. For example, here we could describe that foo is actually a table with 3 rows, and each row has an index from 0 to 2. And then each row, of course, refers to one array element, and each array element has 2 members, and these members then become the columns. Then you could say the first column is denoted by str and the second by val. And then here, for example, we would have the entry Marius. And so on. Now with this high-level description, it's easy to understand what you get here or here when you access a member of an array element. But for determining the number of array elements, where we use this pattern here, it's actually required to have some understanding of the memory layout. But as I said before, you only need to know a few things about the memory layout. Let's go through this line from left to right. You see, we do have a variable. That means in memory, we have a memory location for this variable, for foo. Then we see we do have an array with 3 elements. And that means, actually let me draw this in blue. That means we can divide this memory location into 3 memory locations, one for foo 0, foo 1, and foo 2. And that's actually it. We just have to consider this part to have this description. We don't go further. We don't look into the members of this array elements. And from that we see that this here is the size of one element. Each element has the same size, so it doesn't matter what element we consider. So this is size of foo 0. And this here is the size of foo. And this is all we need to know to get the total number of array elements. And that means with this expression at compile time, we get this 3. And recall that the reason for doing that is that if we later would change this into, let's say, 13, we don't have to change this part. And also recall that size of is not a function, it's an operator, and that this whole expression gets evaluated by the compiler at compile time. So no runtime overhead. But let's go back to simple examples where foo just has this type foo with an uppercase F, so it's no longer an array. And here I first want to review a few things. For example, what you see here is not an initialization of this variable, it's an assignment to this variable. And recall from the last video that you do need this explicit typecast in front of this initializer list. The details that go on behind the scene are the same as you saw in the last video. The compiler generates from that some internal local variable that gets initialized with this initializer list, and this internal variable gets assigned to foo. So actually nothing new that you see here. What you see here is another error message, and here I again want to point out what is actually going on behind the scene. In an assignment, a string is considered to be an array of characters. And because the string itself has 7 characters and then we have this additional 0 terminating byte, this is an array of 8 bytes. And you also see this here in the error message. You see here an array with 8 elements of this type U8. And U8 is short for unsigned integer with 8 bits. But it's actually the same as a character. Actually, this char type is just a type alias for this U8. And I will come back to type aliases later. So back to the problem here. On the left-hand side, we have an array with 12 characters. And on the right-hand side, we have an array with 8 characters. So what we do have is different dimensions on the left and right hand side, or talking in terms of physics, we would have different units on the left and right hand side. So it does make sense to post this assignment. To make it well post, you can typecast the right hand side. Actually, in this case, then this string is again used for initializing a new local, internally generated variable. So here again, the compiler considers this as an initializer list with this single characters. So the same thing as before, together with this 0. Now for convenience, you sometimes don't want to write out this all the time in front of a string. I want to introduce this type aliases that I was actually talking about before for this character type. Now here you see a type alias where I say that string 11 should be used as an alias for this type. And this simply means that, for example, here I simply can write string 11 or here. And that's basically it. But maybe this is also a good opportunity to talk about how the ABC compiler internally uses type aliases. ABC supports a few so-called primitive types, and you can categorize them as types for unsigned integers, for signed integers, and for floating points. For unsigned integers, the only types are actually just U8, U16, U32, and U64. U is short for unsigned, of course, and the numbers refer to the number of bits. So this is a type for an unsigned integer with 1 byte, 2 bytes, 4 bytes, 8 bytes. For signed integers, we have I8, I16, 32, and 64. So the prefix I is used for signed, and this here is 1 byte, 2 byte, 4 byte, and again 8 bytes. For floating points, there are just two types actually, float and double. Float is a single precision and double a double precision floating point type according to this IEEE standard. Now, when you are using types like char or int, you're actually using type aliases. Think of it like that. Char is a type alias for U8. And int is also a type alias, which is actually platform dependent. The compiler checks for which platform it's generating code, and depending on that, it makes this type alias. For my machine, and probably also yours, it's using I32, signed integer with 4 bytes. If you would generate code for an Arduino, then this would be different. There it would be a signed integer with 16 bits, because Arduino only supports for this integer types operations that can be done with one instruction. Let me show you another type alias for unsigned integers, which is simply unsigned. So you can use this also as a type, which will be aliased to the same size that int has, but for unsigned. So on my machine it would be U32. And on an Arduino this would be U16. Same size as int. Okay, but that's it for this topic and this slide. This example is again about this concept call by value and also a bit about undefined behavior. You see that in function main this local variable foo is not initialized. That means the initial value is undefined. Then we call function init and we pass foo as an argument. And call by value means, this concept means that we pass a copy of this value. That means what init gets in X is a copy of foo from function main. And this copy gets overwritten with some data. This means when we come back to function main, to here, foo is still the same as before, which is not initialized. So we see here this strange output, which might be different on your machine. Undefined behavior. Now let's first fix this undefined behavior. You see, here I use a empty initializer list, and that means that this variable gets 0 initialized. Technically, it means that the compiler is replacing this with an initializer list that has actually two components. The first component is another initializer list for the first member for this array with 12 zeros, and the second member would be 0. And with that, you see that at least we now have a defined behavior. The string is empty and the value is 0. But now we have to deal with the actual problem. What we want is that after calling function init, this variable foo should have been initialized by this call. And in order to achieve that, we have to use pointers. So instead of passing a copy of foo, we pass the address of foo. That means what function init gets is actually a pointer to a variable of type foo. So we also have to change here the declaration of this parameter x. So this changes into x has the type pointer to foo. And then in the function body, we have to write some data to the end of this pointer. That means here we have to replace x with what is at the end of x, and there we can access the members, for example, .str or .val. And this is what I have here on the next slide. And here I want to walk through the code by also looking into the memory locations. So we start here. That means we have a memory location for foo. Let's draw it here. So this is the memory location for foo with all its members. So we have here foo.str, here foo.val. Then we pass the address of foo and enter function init. So that means now we are here. Now we have a new variable on the stack, x, which is a pointer. So let's say this is the memory location of x, and the content of this memory location is the address of foo. So we can think of it as pointing to the left edge of this memory location. And this means that if you use something like asterisk x, you refer to what is at the end of the pointer. That means you actually refer to this memory location. So you also can say this here is now equivalent or identical to asterisk x. That means this here is identical to this member, and this one here to this member. So that's basically it. After you return to function main, so when you're here, then this memory location is no longer valid, but it doesn't matter because init has done its job. It has changed the content of this memory location. And that's it. And then you see initialization works. So that's almost it for this video. What is actually left to tell you is that there is a more convenient notation compared to what you see here for this dereferencing x and then accessing a member. What you can write instead of asterisk x within this parenthesis followed by .str is x followed by an arrow followed by the name of the member, str. This is basically treated by the compiler as if you would have written this. If you use this notation with the asterisk, you have to use this parenthesis because you have to express that first the pointer should be dereferenced, and then at the end of this pointer, this member str should be accessed. Whereas in this notation, the compiler reads this from left to right, and it treats this as at the end of this pointer, consider this memory location for the member str. And With this arrow notation, this code, in my opinion, looks a little bit nicer. But you can use both notations, of course.